Schrödinger's equation dictates the behavior of all matter, yet we typically only observe effects like quantum tunneling, where a particle passes through a barrier, only at the subatomic scale. In everyday experience, a millimeter-sized circuit remains bound by classical physics. This divide exists because of decoherence. Macroscopic objects are constantly bombarded by heat, radiation, and vibrations. These interactions are so strong, they force fragile quantum states to collapse instantly into classical behavior. The 2025 Nobel Prize in Physics recognized a series of experiments that bridged this gap. The researchers set out to isolate a single macroscopic variable and force it to obey the laws of quantum mechanics. Clark, Devet, and Martinez proved that quantum behavior is not restricted to the subatomic world. To bridge these scales, they took an object visible to the naked eye, isolated it from its classical environment, and forced it to behave like a single subatomic particle. The team utilized a millimeter-sized electrical oscillator circuit and cooled it inside a dilution refrigerator. They reached temperatures of 20 millikelvin, significantly colder than the vacuum of deep space. At these temperatures, the metal becomes superconducting. The chaotic gas of electrons slows down, forming Cooper pairs. These condense into a single quantum fluid, a Bose-Einstein condensate. Now, the entire fluid moves through the circuit as a single entity, with zero electrical friction to dissipate energy. By unifying billions of electrons into one state, the researchers isolated a single macroscopic variable, the gauge invariant phase difference, or delta, of the entire condensate. By freezing out thermal noise and binding electrons, the team removed the effects of classical thermodynamics, leaving the circuit ready to be tested for pure quantum behavior. Standard electrical circuits present a specific challenge for quantum control because they function as harmonic oscillators. In a harmonic oscillator, the potential energy well is a perfect parabola with evenly spaced energy levels. If a microwave frequency triggers a jump to the first level, it simultaneously stimulates all other transitions. The system jumps uncontrollably, appearing entirely classical. Physicist Anthony Leggett provided the theoretical framework for solving this, proposing that researchers examine how dissipation and friction affected quantum processes in macroscopic systems. To circumvent the limitations of the harmonic oscillator, the team replaced the standard inductor in their circuit with a Josephson tunnel junction. A Josephson junction consists of two superconductors separated by a thin insulating barrier. Because Cooper pairs must tunnel through this barrier one by one, it introduces a non-linearity that transforms the parabolic potential into a periodic cosine wave. This non-linearity allowed the team to address and manipulate specific individual quantum states within the macroscopic circuit. The researchers then applied a precise bias current to the Josephson junction. This current tilts the potential energy landscape, creating a metastable washboard pattern of cascading dips and barriers. Inside a single well, the walls flare outward near the top. This ensures the energy levels are no longer evenly spaced. They are non-degenerate. The team fired specific microwave frequencies into the circuit to see if they could trigger distinct jumps between these levels, such as from level 0 to level 1, without affecting level 2.
This graph plots the circuit's escape rate against the bias current. As the microwaves sweep the system, distinct resonant peaks appear exactly where the math predicts the 0 to 1 and 1 to 2 transitions should be. These isolated peaks proved the circuit possessed quantized energy levels. By controlling the geometry of the circuit, the team had engineered a macroscopic artificial atom. The team then conducted the ultimate test, proving macroscopic quantum tunneling. They needed to observe how the system escaped its zero-voltage state inside the potential well. Classically, escape happens through thermal activation. The particle absorbs heat, vibrates, and gains energy to roll over the barrier. In the quantum regime, a particle escapes without climbing. It tunnels horizontally straight through the solid barrier wall, lacking the thermal energy to go over. To identify the mechanism, the researchers used a metric called escape temperature, which compares the rate of escape to the physical temperature of the system. John Martinez identified a significant challenge. A plateau in the escape rate could be a false positive, caused by stray high-frequency microwaves heating the junction. To eliminate this possibility, Martinez designed filters made of coaxial lines packed with fine copper powder. These filters absorbed and dampened external thermal microwave noise by 20 orders of magnitude before it could reach the system. This noise-filtered plot tracks escape temperature against physical temperature. In the classical regime, the line drops linearly. However, at 25 millikelvin, the data decouples. The escape rate flatlines, forming a perfectly horizontal plateau that remains constant as physical temperature continues dropping. This plateau, achieved in an environment devoid of thermal noise, provided conclusive evidence that the macroscopic object was quantum tunneling through the barrier. The team matched their experimental data to theoretical predictions using parameters measured directly within the circuit without relying on mathematical fitting. In a natural hydrogen atom, properties are fixed by universal constants like the electron's mass. In the laureate system, vital parameters like inductance and capacitance are determined by the physical geometry of the circuit design. Because these properties are geometric, they can be deliberately engineered, calibrated, and scaled. By moving from the observation of natural particles to active design, the team established the practical framework for the field of quantum engineering. The direct technological descendants of the 1985 experiment are the transmon qubits that power today's superconducting quantum processors. While stable quantum states can now be engineered, the primary hurdle for scalability remains managing macroscopic errors and dissipation in larger systems. Using the foundational understanding of macroscopic tunneling, physicists can now map and correct these complex quantum errors using standard probability statistics. The work of Clark, Devet, and Martinez established the physical foundation required to build modern quantum computing hardware. Their success demonstrated that the boundary between the classical world and the quantum realm is not a matter of size, but a matter of engineering.